So there are a lot of proof techniques available. One of them applies to when we have infinitely many statements that we want to simultaneously prove. Okay, so how could you possibly prove infinitely many statements? Well, let's take a look at one particular example. One of those has to do with summations. And if you remember, the summation sign just means add up. And it's going to add up all of these numbers. This is the argument. It's going to add up all of these numbers called I. And I is going to go from 1 up to n. Okay, so that would basically mean that if for example, if you had n equals 2, then first of all, I would be set at 1, and I would go from 1 to 2. And every time you write the first term, okay, so that's when I is equal to 1, and then we're going to add to that, and now we increase the value of I to the next index, which is 2, and then we'll add those two together, and we get 3. What we're claiming is that the sum that we end up with should be the same result that we get if we simply take n, multiply it by 1 more than n, and divide that result by 2. Well, let's check it out. Let's see if that works. So in this case, n is 2. And if I take 2 times 2 plus 1 over 2, it's 2 times 3 is 6, over 2 is 3. And if you notice, we get the same answer whether we add or we compute this little formulaic value. Okay, now if n was 3, that would mean that I would start at 1. Okay, so that means here we would just insert 1 for I. And then, okay, we're done with that value of I, so now we add to that. Now we increase the value of I. Okay, now the next value of I would be 2. Okay, so this term would be 2. And then we're going to add to that. We're going to keep on going until I hits the value of n, in which case we are talking 3 in this moment. So now I is equal to 3, so we add 3 to all of that, and that's going to give us 6. Okay, well, you can see that if we went up to 100, we would be adding 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the way up to 100, and that's 99 addition signs. So the convenience of using a formula is that regardless of how big your value of n is, this equation is saying that for any given value of n, for any positive integer, that you can compute what the sum is going to be just by plugging in the value of n. So take 3 times 3 plus 1, divide that by 2. 3 times 4 is 12, divided by 2 is 6, and lo and behold, we again get the same number. Now, that's already 2 different statements. If you notice, what we established here was, in the top, we established that the sum of all the i's beginning at I equals 1 and going up to I equals 2, that does indeed give us 2 times 2 plus 1 over 2. It gives us the same result. So that is one statement, and we can call that statement P of 2. Okay, so in this case, this is just our value of n. So this generates one individual equation. But when n becomes 3, now we have a different equation. And it's still the same structure, but it's a different equation because now it's I from 1 all the way up to 3 of the sum of these I values. And we've established that that is equal to 3 times 3 plus 1 over 2 gives us the same result. So this is what we would call P of 3. And you can see that each value of n is going to generate a new n value. So maybe we want to prove P100, and P100 would be the statement that the sum of the first 100 integers, positive integers, is equal to 100 times 100 plus 1 over 2. But we would like to establish one proof rather than to have to go each of these individual cases, because you can see this formula is useless if you would have to prove it every single time you needed to use it, because at that point you might as well just do the addition, and the shortcut isn't going to do anything for you if you can't guarantee that it's always going to work. So we want to prove this for all integers n greater than or equal to 1. Now, by the way, 1 would work. It would just you'd just stop at the first term. If I went from 1 to 1, then it would just be 1 plus nothing else. So because we want to do this, that means we want to prove P of 1, we want to prove P of 2, P of 3, and so on, forever and ever and ever for every single integer. Now, of course, there are infinitely many integers, so there's infinitely many variations of this equation. So a direct proof will not work here. There's no way that we could just start off proving this for just any value of n, because, hey, n could be any integer, and how do we establish a connection between a bunch of things we're adding together and this sort of what I like to call a reduction formula, a formula that does that for us more quickly. Now we'll come back to this, but first of all, you might be thinking, right, well, what about statements like the sum of any two even integers is even? Isn't that also filled with infinitely many statements? And the answer is yes and no. Okay, it is infinitely many statements in the sense that there are infinitely many integers, even integers that can be chosen. However, the structure of an even integer is always the same, regardless of which even integer we're talking about. So there is consistency across all even integers. For example, we know that 4 is equal to 2 multiples of 2, 6 is equal to 3 multiples of 2, 100 is equal to 50 multiples of 2. And the thing that we always know about an even integer is that it's always an even integer, even number, is 2 times k for some integer k. Okay, that integer is different, right? Because it depends on what value, what even number you're talking about. The number of copies of 2, the number of integer multiples of 2 could be different, and that's what we're saying here with k. Probably should have written this as 2 times 2 like this, and then 2 times 3, and 2 times 50. You can see that in this case, the value of k is going to be different from one even integer to the next. But the thing is that if I'm talking about summing two even integers, well, I could just say let integer 1 be of the form 2k, and let integer form, the second integer be of the form 2j, just so that we're not saying they're the same even integer. Okay, so k and j are some integers. And then when we add these two even integers together, we see we could just factor out a 2, regardless of what those even integers are. And hey, by the closure property of addition, we know that if we add together two integers, we get another integer. And so, hey, we have that the sum of two even integers generates a new even structured number. So while there are infinitely many choices, it's really just one statement. But the difference up here is that these are different equations. They involve the same structure, but each one has a different number of terms, first of all, right? If n is 100, it's going to have 100 terms. And so for n equals 3, we only have 3 terms, and they're different. So we do have infinitely many statements. And the question is, how do we do this? How do we prove infinitely many statements in a minimal number of steps? Now that method that we use is called the method of induction, and we'll see how that works in the next video.